I've got this friend who has this really nice laptop bag. Perhaps it's from Italy or somewhere like that. And she always has it loaded up with all sorts of gear she needs for business travel, so she can just grab it and go. It's pretty slick. Except this one time, she left on a business trip and was in the air, think 30,000 feet at least, and found one slight issue. She forgot to put the laptop in the bag. Yeah. Oops. Finding problems too late can cause enormous delays in engineering projects. When you're doing long physical design cycles on a complex chip, you'd like to catch those errors early in the process, before you've spent all the time to get to the very end of the verification flow, and have to find out that you have to start all over. Or take the flight back from halfway to your destination and then a red eye in order to get there by the next morning with like my friend had to do with her business trip. Hi, I'm Amelia Dalton, host of Chalk Talk, and I'm here today with my laptop talking to Christen Decoin from Synopsys about accelerating physical design productivity by catching problems earlier in the process. And before we get started, don't forget to click that link. There you can find more information about this topic from Synopsys. Hi, Christen. Thank you so much for joining me.
Hi, Amelia.
So I'm sure I'm not alone that my team's biggest challenge in getting to tapeout is physical verification. We need to find ways to make our physical verification faster and more predictable. And we need to find ways to shift left with our verification and get feedback earlier than later in our project.
Yeah, that's correct. And for a long time, physical verification really focused on the sign-off, on the last run. But if you look, our customer experience is that you have to look at the full physical verification cycle, and it's a question of productivity. And by shifting left, if you only do, you block sign-off, chip integration, final sign-off, and you don't have a way to optimize that, you will spend a lot of cycle. And we think that there is a way to decrease the physical verification cycle to have block sign-off done early and correctly at the sign-off level, then a better chip integration solution, and also a final sign-off.
Okay, so you mentioned fixing errors earlier. One of our biggest issues is finding bugs way after they occur and then having to redo all the downstream design work to fix them. How would you help me with that?
That's what we call InDesign. Physical verification was signed off for a really long time. And then about 8 years ago, people are looking at InDesign more and more as something to clear error early in the design flow. We can do, automatic repair in a physical in place and route implementation flow. We can also do timing-aware sign-off field, which allow you to have a better impact on your timing result using field. And then if you have you use a foundry that use pattern matching kind of flow for hotspot prevention, we can also do that in design. And the advantage is you stay within your design environment, and that gives you a better productivity altogether.
Now, Christen, our SOC designs are big, ginormous, and we run into serious integration problems. How can we find and fix those issues without running full-blown DRC, which takes forever and gives us enormous error reports?
Again, if you look at the physical verification time and solution, there was a lot of focus on the sign-off. They still focus on sign-off. And then InDesign about a decade ago started to be something that people were worried about. Chip integration was always a problem, but there was never a solution. If you look, it's easy. Quote, double quote, customer will say it's easy to run sign-off and clean design. But when they do the first sign-off on the chip first integration and they have block overlap issue, feed overlap issue, and a lot of other, major integration issue, runtime are really long, and there was no solution so far for that. Now, we came up with this Explorer mode that allow you to look at the fundamental issue of your chip integration, and that gives you a 5x speed up, and you can do that with 5 times less CPU. And it's great, and we also have a special debugging environment called DRC heatmap that doesn't show you one error by one error, but give you overall understanding where are your macro issue when you do your first time chip finishing.
Cool. Okay. So, Christian, how well does this Explorer-based flow work in practice?
When we develop this flow, we work with some customer. And what was really interesting is we work on a traditional full chip GRC sign-off physical verification cycle. And at the same time, we work with the Explorer plus sign-off kind of usage. When we run the first design after the first integration, it ran for several days, yield 50 plus billion errors, took a lot of machine, 250 plus CPUs. And in the same time, we run Explorer on one single 32 CPU machine, run in 9 hours, yield 11 billion error, which are all linked to this foundation issue. But it was way quicker for the design group to debug, and then they could do a second run quicker, and pretty quickly they could start to switch to the sign-off run. What is interesting to see is that really quickly overnight you could find the major issue thanks to the GRC heat map. And we were able to decrease the physical verification cycle by 2x. But what surprised us is the customer run more run with this Explorer flow. Because they could do so many overnight runs, they run a 50% more GRC run that they would have done with a normal sign-off.
Wow.
Pretty interesting to see how people change their habits.
Absolutely. Okay, so even when we're doing our best at catching and fixing errors early, we still have to do a huge sign-off verification. So, Christian, what is being done to make that process faster and better?
For years, the focus was on the brute force how to make GRC faster. Now we look at smarter way to do that with InDesign and the Explorer mode, but we still need the brute force because the tapeout GRC is the last thing that blocks you tapeout. And what we did is IC Validator as a massively parallel processing that is the best in class to be able to spread across multiple number of machines. It's fully distributed. And we demonstrate scalability on thousands of CPU, which is really good. Meaning, if you have a customer who have a large farm and you really want to add additional CPU to get a faster turnaround time, you can do that.
Okay. So with these giant arrays of servers crunching away on our DRC runs, it seems like just keeping all the machines working together is a major challenge.
Yes, and then you have to look at the loading of the machine. All the machine could be different size. And we have a dynamic scheduler that really look at what are the machine available, what memory is available, and how many command and computation to send to each machine. And if you see that the machine is going to be overloaded, it's going to reschedule this command on different machine. And also really important is, are you resilient to failure? Are you fail safe? If your machine crash down, is your job done? Not with our dynamic scheduler. It will see that the machine shut down and it will restart the command on a different machine.
Now, Christian, not all servers are alike and not all batch jobs are alike. Is there anything we can do to match the tasks better to the capabilities of the hardware?
Yes. When we are talking about distributed processes and the scheduler will look at what memory is available or what is available on your machine and will schedule as many commands as possible. Meaning if you have, let's say, a 512 gigabyte machine and you need to run 380 gigabyte out of that, it will use all these. And some people will say, yeah, but that's use a lot of memory. And then what we did, we demonstrate that if you have a 256 gigabyte machine, we can run on 256. The scheduler will hold some of the command and schedule them later, meaning you will have a little performance impact, but will be able to fit in that machine. And we even managed to push down to 128 gigabyte. And it's about 10% impact, but that's great. You can also ask the tool to only use 250 gigabyte on the 512 gigabyte machine. Like that, you can have to run concurrently. But this is really the dynamic scheduling allow you all this flexibility thanks to this distributed architecture.
So with multiple engineers and teams using the same server resources, Christian, we get into issues of when to start our runs so we don't collide with other people's work. How can you help me with that?
There's that fact, and there's the other fact that, the usual, I would say, physical verification tool will have to wait that all the machines are available to start.
Right.
And we had a customer example that uses farm on a tapeout mode and had to wait 7 days to get all the 256 CPU available. With IC Validator, we have this elastic CPU management where we can start right away and we can increase the number of CPU each time they become available. And that's create a huge advantage. While the customer was waiting 7 days for this run to start, we were done like 3 or 4 runs. Because when the CPU start to ramp up, we were able to use the CPU as they came along. And that gives us enhanced productivity again. I want to add, in the good old time, if you did physical verification evaluation, you were looking at 8, 16 CPU. That's easy to get, right? And I would say evaluation were really based on 8, 16, 32 CPU. Now we see more and more customers doing real life evaluation benchmark. They throw you on their farm what they're going to use at tapeout to see if not only you're really good, but how you can use the CPU in the most appropriate way.
Okay, so with our enormous designs on the smallest of small geometries, we often need more servers than it's practical for us to own. Can we use cloud-based resources to make our capability more elastic?
Yes, and if you look, cloud for EDA and physical verification have been talked for a really long time. The ecosystem opened up the last 12 months, right, with 2 major foundries supporting cloud usage for EDA vendor. And with this exploding runtime due to the chip size increasing at each node and the increasing DRC complexity, the need when you do this final sign-off run for number of CPU is escalating. And then we have more and more customers who are looking at cloud. Not only the small guys, by the way. If you're a startup in AI, for sure you don't have the farm to run 512 CPU. Then the cloud makes sense. But we see also a large semiconductor company using the cloud to extend their farm and use that as a hybrid where they can use their farm and extend the farm when there's a peak need with the cloud.
Sure, that makes sense. Okay, so you use the term cloud ready. Help me understand what's exactly involved in that.
Yeah, I mean, the cloud, if you look at Amazon Web Service and Azure and Google, they have a lot of things that it would be great if you could use the flexibility they give you. They talk about elasticity. That's something that we're really interested in using. And I see Validator as this capability to add CPU on the fly, as we discussed earlier, but you can also remove it. Meaning, if you have a special price at different time of the day on the cloud user that you use, you could say, I'm 256 CPU now, but I know from 12 a.m. till 6 a.m. I have a cheaper CPU availability. Then I can add 512 CPU additional and remove them when the price is increasing. And doing that, on the fly without having any impact on the runtime is really cool. Scalability is another one, right? You don't really think about going in the cloud if you run 12 CPU. But if you need 256, 512, 1024 CPU, cloud is perfect. Smaller memory requirement, we talked about that a few slides before that. That's pretty interesting because the biggest machine you have, the more expensive is in the cloud. Meaning it's better to have 10 machines of 128 CPU than a big machine of 1 terabyte memories because it's cheaper. Then if you can accommodate smaller memory requirement, that's also a big advantage for the cloud. And then we talk about the ecosystem support, which is there, with foundries, IP provider, and cloud provider working together to make this a reality for the customer today.
So you guys have done a lot to make your sign-off tools be effective for cloud-based deployment, right?
Yes, cloud-ready, physical sign-off, and we even use another term, which is cloud-friendly.
Okay.
Because you can be cloud-ready and run, but if you have a technology that's architected to run on 1,000 plus CPU, we have even done some trial on 2,000 CPUs. If you have the building memory awareness where the scheduler can make sure it's used at the best, the CPU available, the elastic CPU management, we talk about adding CPU when you need, remove when you don't. And then the intelligent file management to balance disk memory speed in multi-host environment. And of course, all these certified by the foundries, right? It's really important.
Very important. Okay, so we have covered a lot today, Christian. Can you give me a summary of your main points?
If you look right in physical verification software, you're looking for something that is comprehensive. And IC Validator has all the pieces that is needed for a comprehensive solution. Need to be scalable for the final sign-off run, which is really important. That's push you through the gate. Has to be cloud optimized for most of these customers that are looking more and more at the cloud. Robust debug tools, not only for DRC and LVS, but also for the Explorer. If you provide a new way of looking at physical verification, you have to find a new way how to debug faster. Otherwise, you cannot talk about productivity. And then it has to be found with certified, right? That's the base.
Okay, well, I think that's all I have time for today. Thank you so much for joining me, Christian.
Thank you, Amelia.
And before we go, you didn't forget to click that link, did you? There you can find even more information about physical design productivity from Synopsys. For Chalk Talks, I'm Amelia Dalton from eejournal.com. For more Chalk Talks, head on over to the Chalk Talk section of EE Journal. Can't miss it, it's right across the top. Or head on over to YouTube, keyword EE Journal.